Alright, so we're going to address in part 3 here how we calculate these values that you see on the periodic table, the 47.87 for titanium, 55.85 for the iron, the 14.01 for the nitrogen. These are called atomic masses, and they're an average, but they're weighted average, and they're weighted towards the most common isotope. So I'm going to take you through how to calculate the value called atomic mass. It was developed for reasons which we've already discussed. The value of the mass of a proton is way too small for us to talk about it in terms of grams. So they developed an AMU system, and every system of measurement needs a standard. So carbon 12, 6 neutrons, 6 protons, mass number of 12. Carbon 12 was assigned a mass of 12 AMUs, and that is the standard for the system. In other words, all other elements are based on their relationship to the size of carbon. So hydrogen is about a 12th the size of a carbon atom. So if it's 1/12 the size, that means it's 1 AMU. Hydrogen's 1 AMU, and carbon is 12 AMUs. All right. So how do we go about actually getting the value mathematically? Well, let's take this example. All right. The isotope abundance for element X. Now, element X is an actual element, but we're keeping it secret so that we can do this problem to figure out the value. All right, so it has apparently 2 isotopes, X6 and X7. Now, you'll notice the Z value is absent because if I gave you the Z value, you'd already know what element it is, so I left this blank. All right, but we know that the mass number of this isotope is 6, and we know the mass number of this is 7. The AMU value of each isotope is listed, 6.015 for element X6 and 7.016 for element X7. And then we have what's called percent abundance. And basically what that means is, let's say you had a 100-gram sample of element X. On average, 92.5% of it is going to be composed of isotope X7, and only 7.5% is going to be composed of X6. So what would that tell you about the average? Well, if it's a weighted average, and it's weighted 92.5%, quite a bit in this direction, then our overall average is going to be closer to 7.016 than it is to 6.015. If the numbers were flipped, 92.5 up here, 7.5 down here, then the overall average would probably be closer to 6. All right, so let's calculate the value. Okay, what we're going to do first is we're going to take our percentages and we're going to convert them to decimal numbers. Well, of course, that's very easy. We take our 7.5 and we basically move the decimal over 2 spaces or divide by 100, whichever way you want to do is fine, and we get 0.0175. Then we take the 92.5 and we move it over 2 spaces to the left and we get 0.925. So you change your percentages to decimal numbers. Then you take those decimal numbers and you multiply them by the AMU mass for each isotope. So for element X6, the value is 6.015. Its percent abundance was 7.5%. We've converted it to 0.075. And we multiply that out and we get 0.45. Then for element X7, or isotope X7, the value was 7.016. And it was 92.5% abundance, which means we're going to multiply those two together and we get 6.49. And the last thing you're going to do is you're going to take those two values and you're going to add them up. 0.45 plus 6.49 gives us 6.94. Now what we can do is we can take that number 6.94 AMU and we can go back and look at the periodic table and we can figure out what element we're talking about. And as you can see, 6.94 is the atomic mass of lithium. And that means that lithium, from our example, must have 2 different isotopes. We have lithium 7, and we have lithium 6. Well, what are we going to put for the Z value? Well, they both have an atomic number of 3. So we're going to put 3 right there. We can put 3 right there. Or we could just write them as lithium 7 and lithium 6. And that's how you go about calculating the atomic mass unit. In other words, the average number. Now, if we go back and we look at our example from the notes, we notice that the isotopes were only listed as 2. Well, if you had 5 isotopes, then you'd have to do the same thing, but it would just take longer. It's not like the math's any harder. It's just a matter of doing more simple math to get the total. So if we had 10 isotopes, we'd have to do this 10 times and then add all 10 products up at the end. So depending on the element, the more isotopes you have, the more work you have to do, but it's really not that difficult. All right, so that's part 3, and part 4 will be coming soon.